You've seen them, right? Those bags of fertilizer, just a bunch of numbers and chemical names. We all know they make our plants grow, but what is actually going on down in the dirt? It's this incredible, complex chemical dance, and that's exactly what we're going to break down today.
Yeah, this is really the big question, isn't it? What happens when that stuff hits the dirt? Because, it's not as simple as just feeding the plant. Oh no. We're talking about a whole cascade of chemical reactions that can change the very nature of the soil. And that can be a good thing or a not so good thing.
All right, so here's our game plan. First, we'll cover the basics. What are chemical fertilizers? Then we'll dive into the big three: nitrogen, the growth engine; phosphorus, the root builder; and potassium, the plant protector. And to wrap it all up, we'll look at the aftermath, what's left behind in the soil long after the plants are grown.
Okay, so let's jump right in. First things first, what even is a chemical fertilizer? What are we really talking about here?
Well, at the end of the day, they're basically factory-made, super concentrated meals for plants. Imagine a high-energy protein shake instead of a slow-digesting meal. And because most of them dissolve in water really easily, they give plants this incredibly fast hit of nutrients, getting to work almost instantly.
So you can basically group them into two main buckets. You've got your straight fertilizers; they're specialists, delivering just one single nutrient. And then you have compound fertilizers, which are more like a multivitamin, a cocktail of different nutrients. We're going to focus on the big three superstars of the nutrient world: nitrogen, phosphorus, and potassium.
All right, first up, let's talk about the king of the castle, the undisputed champion, nitrogen. This is the stuff that gives you that deep, lush green growth. It's the growth engine. And the number one way farmers get it into the soil? A little white pellet called urea.
And this number right here, this is exactly why urea is so dominant. 46%, that's the minimum amount of nitrogen packed into it. It is by far the most concentrated solid nitrogen fertilizer out there, which makes it super efficient to ship and spread all over the world.
Okay, but here's the crazy part. When you put urea on the soil, the plant can't actually eat it right away. It's like it's locked. It needs help from the microbes in the soil to unlock it. First, they perform a little magic trick and turn it into ammonium. Now, some plants, like rice, are happy with that. They'll slurp it right up. But for most plants, there's another step. The microbes have to convert it again, this time into nitrate. That's the 5-star meal most plants are looking for. But, and this is a big but, this whole process isn't 100% efficient. Some of that precious nitrogen just gets lost. It can wash away or even escape back into the air as a gas.
So this gives farmers a choice, right? They can go with an ammonical fertilizer. Now, this one tends to make the soil more acidic over time, but the upside is that it kind of sticks to the soil particles so it doesn't wash away easily. Perfect for something like a flooded rice paddy. On the other hand, you've got nitrate fertilizers. These make the soil more alkaline, and they're like fast food for plants, ready to be absorbed immediately. The downside? A good rain can wash them right out of the root zone. It's always a trade-off.
But wait, there's a villain in our urea story. Its name is Muriate. See, during the manufacturing process, if things get a little too hot, this toxic compound can form, and it's nasty stuff. If you have more than about 1.5% of it in your fertilizer, it can actually stop seeds from even germinating. So for fertilizer companies, checking for Muriate is an absolutely critical quality control step.
Okay, moving on to nutrient number 2, phosphorus. If nitrogen is the growth engine, think of phosphorus as the root builder. It's all about creating a strong, healthy foundation for the plant. It's absolutely essential for root development, but also for getting those beautiful flowers and fruits.
Now with phosphorus, the name of the game is solubility. How easily does it dissolve? You've got your water-soluble types, like single superphosphate, which are ready to go immediately. Then you got ones that are only soluble in citric acid. That means they need the plant's own roots to release acids to break them down, kind of like a slow-release vitamin. And at the far end of the spectrum, you have something like rock phosphate, which is basically insoluble and takes ages to become useful to the plant. So which one a farmer picks really depends on their soil type and how fast their crop needs that phosphorus hit.
And that brings us to our third member of the big three, potassium. I like to think of potassium as the plant's bodyguard or protector. It's not really part of the building blocks of the plant itself, but it's the general manager. It regulates everything, helping the plant fight off diseases, survive a drought, and, really importantly, produce better quality fruits and veggies.
Now, when you're looking at potassium fertilizers, it pretty much boils down to a choice between two main players. First, you have Muriate of potash. It's the most common one out there, it's cheaper, and it's got more potassium packed into it. But it has a secret ingredient, chloride. Then you have sulfate of potash. It's pricier, a little less concentrated, but its main selling point is what it doesn't have. It's chloride-free. So why on earth does that even matter?
Well, it matters a lot, because for a handful of really important, high-value crops, chloride is a total deal-breaker. We're talking about things like tobacco, potatoes, tea, and coffee. For these guys, the chloride from urea to potash can wreck the quality of the final product. It can mess with the taste, how well it stores, you name it. So for these specific crops, farmers have no choice. They have to shell out for the more expensive, chloride-free stuff.
Okay, so we've seen how nitrogen, phosphorus, and potassium are like rocket fuel for plants. They give them this massive boost. But what about the after? After the plant takes what it needs, what happens to what's left behind in the soil? This, my friends, is where our story takes a bit of a turn.
And this is such a critical question, because you have to remember, we're not just adding this stuff once. It's happening year after year, season after season, and all those highly concentrated chemicals, they have a cumulative effect. It's not a one-and-done transaction with the soil.
Let's just take one example here. So when a plant sucks up the ammonium from a fertilizer, like ammonium sulfate, it kicks off a chain reaction in the soil. And the byproduct of that reaction? A whole bunch of hydrogen ions are released. And when you flood the soil with hydrogen ions, you get one result. The soil becomes more acidic.
So let's break that down. It's basically a three-step process. Step 1, the fertilizer adds ammonium. Step 2, those hardworking soil bacteria get to work, and in the process, they release hydrogen ions. Step 3, these hydrogen ions are like little bullies. They literally push essential nutrients like calcium right off the soil particles and out of the way. The end result? The soil gets more acidic and, over the long haul, less fertile.
And this really gets to the core of the problem. There's a quote from our source material that just nails it. It says, "In the race to increase production, farmers are using fertilizers indiscriminately. The adverse effects on the physical, chemical, and biological properties of the soil are becoming clear." It perfectly captures this tension, right? The battle between getting huge yields now versus maintaining healthy soil for the future.
Which brings us to the final and maybe the most challenging question of all. How do we feed a growing world without starving our soil? There's no doubt that chemical fertilizers are an absolute pillar of modern agriculture. We rely on them to feed billions of people. But as we've just seen, that power comes with a price tag for the very soil we depend on. And figuring out how to strike that balance, well, that's one of the biggest challenges of our time.